Okay, let me start with the rudimentary theorem. For every R, there is an N such that when we look at a connected graph, G of order at least N, then G contains, I don't know, something like a KR. Right? So what can we force? If G has a vertex of large degree, so the idea is again that every connected such graph G contains something, or the complement will contain something. Right? But we're now assuming a little more about G. So if G has a vertex of large degree, then let's look at the neighbors. Many, 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 many neighbors. These many, 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 many neighbors have either many adjacent pairs or many non-adjacent pairs by Ramsey. If many means at least the Ramsey number of R. So large is the Ramsey number of R. Then, if there's a KR in here, one possible result of this, then we have a complete graph together with V. So we have a KR plus 1. Let's just say KR. Or we have R independent vertices. Then we have a star, K1R, and we have that induced, right? Otherwise it makes no sense. It's in this KR plus 1 already. Okay, so if there's a vertex of large degree, and this is the very, very concrete definition of large, depending only on little r, then we have one of these two outcomes. Now, what if not? Case 2. There's no vertex of large degree. So one usually says in Ramsey's theory that the max degree is bounded. Right? So if we have some max degree smaller than this, that's the bound that I'm talking about. No vertex has this degree, so all vertices have degrees smaller than this Ramsey number. Then the whole graph just has to be big enough in order for there to be a long path. Right? We have only delta edges coming out of this. We have delta edges coming out of each of its neighbors. So if we go a distance of, say, R edges deep, then we have something like delta to the r many vertices. Right? Delta times delta times delta times delta r times. Okay, so just make G bigger than that. And if G is bigger than that, then either it has a vertex of large degree, or it doesn't. I mean, if it doesn't, it has a long path. Okay. And this path is also induced, so it doesn't have any chords, doesn't have any shortcuts. Yeah, so isn't that a cute little thing? We can say a little more than getting KR or R independent vertices if the graph we're looking at is connected. So that's 941. Questions? Good. Okay. 942. Same for two connected. So let's assume that our big graph is true connected and see what we can say. Case 1. There's a vertex of large degree. V. Now, delete it and look at the rest. G minus V, and that is still connected. Right? So inside this big connected graph, big because even these vertices are many, inside this big connected graph, take a minimal subgraph that makes these vertices connected. So that is going to be a tree. Let's call that T. That either has a vertex of large degree, say this one here, in which case we just follow the edges incident with this one vertex all the way on to this set. And what do we get? Oh, I should have had you guess first what the typical, or archetypical as I'm going to call them, two connected graphs are. Those two connected graphs that must occur, or the types that must occur in any two connected graph if it's large enough. So here, every connected graph will contain one of these three as an induced subgraph. Now, can you think of what every two connected graph must contain? Well, come on. I mean, yes, cycles. So, yeah?
I have a question.
Sorry.
Couldn't this tree just be like a path through all the neighbors of B? Then there wouldn't be...
Yes. We're in case 1.
Ah, okay.
Okay, so cycles, every two connected graph has a cycle, or we know that. So is the analog of this true for cycles, that for every R, every two connected graph, if it's large enough, contains a CR, or a cycle longer than R, say? Is that true? For every R, every two connected graph contains a cycle of length at least R, if the two connected graph is big enough. No. Right? So this vertex might be adjacent to all those. Right? So the other option is a K true R. And I said cycle of length at least R, and here also we don't get a K true R, but a subdivided K true R. Okay, that was case one. Case two, this tree does not have a vertex of large degree. Then it has a long path. And this long path may be assumed to join two leaves, to connect two leaves. If you take a path in a tree, you can extend it until you get stuck at a leaf. Right? So the other possibility is that there's a very long path in that tree between two leaves. And that is going to be our CR. Okay. Questions? Are you happy now? That's good. Okay. Right. So when I said that these graphs are archetypical for connectedness or for two connectedness, what exactly did I mean? Well, the theorems sort of say something like that. Every large enough connected or two connected graph contains one of these very few types, therefore typical, of subgraph. We can't tell in advance which of them, so there are arbitrarily large two connected graphs that don't contain K2Rs. For example, the long cycles. And there are arbitrarily large two connected graphs that don't contain long cycles, for example, the K2Rs. So one of these two types must occur in every large enough connected graph, a two connected graph. But we can't do with just one of these types. And that is because the other type is also a class of arbitrarily large two connected graphs. And the two don't contain each other. That's why we can't throw one of them away. We'll formalize that in a moment. Let me just state the theorems for 3 and 4 connected. For 3 connected, we need K3R, and our wheels as minors. So we started with induced subgraphs here. If we don't insist on induced, we can do away with KR. So if we just ask which subgraphs will necessarily occur in every connected graph, if it's large enough, then a big star or a long path is a sufficient answer. Right? Because this does contain both these, so we don't need it anymore if we don't insist on induced. And that, incidentally, reminds you of the infinite little corollary we had for the infinity lemma. Right? Every infinite locally finite graph contains a long path, an infinite path. Or every connected infinite graph contains an infinite star or an infinite path. And that's the same here, just quantify, with finite numbers. Right. So here we started with the strongest possible relation induced graphs. We can get a slightly simpler theorem for just subgraphs, not induced subgraphs. Here there are too many even subgraphs to list, and therefore we just listed topological types, and there we had only two. And now for 3 and 4 connected, we need to get even weaker and are just able to list a few graphs, 3 connected graphs that will appear as minors. And our wheel is simply a cycle with an additional vertex adjacent to everything on that cycle. We had that in the wheel theorem, in Tutt's wheel theorem, although it didn't occur in the version that I gave you. Okay. Right, and for G4 connected, we get K4R. Are double wheels. Right, we take a long cycle and we add 2 vertices, 2 sort of hubs. Then we need something called crowns. And Mobius crowns. As minors. You can look up in the book what these are. Have I forgotten any? No. Okay. So let me just state those, but we proved these two explicitly. And let me now go to formalize this. So formalize what I mean by archetypically connected, archetypically 2 connected, or 3 or 4 connected. So let me just give you the idea by considering something that isn't in fact true. So if it was true that all connected graphs, as long as they're large enough, must contain arbitrarily large stars, how could we formalize that? Well, we could take the class of all stars, or set of all stars, all of them, infinitely many. And then we could say, consider any infinite set P of connected graphs and I'm saying any infinite set because I want to emulate somehow the notion of any large enough connected graph. Then, if it was true that every large enough connected graph contained any given star, then we could start with any given star and find in this particular very, very sparsely chosen but yet infinite set of connected graphs, some in which it is contained, right? Because we're assuming that every large enough graph, if it's connected, contains any given star. Right? That's false, but I'm assuming it to illustrate the idea. So if it's true that every star, no matter how big, so we can begin right up here, very, very high, with a big star, can be found in any connected graph as soon as that graph is large enough, then since we have an infinite set here, there will be large enough connected graphs in there. And we can find this inside some suitable graph there. So each of them can be embedded in something on the other side. And in that case, I want to write that the class of stars, or the set of all stars, is at most this set P of connected graphs. So what's the formal definition? That P and P prime be infinite sets of graphs. Then P less than or equal to P prime is going to mean that for every G in P, there exists a G prime in P prime such that G is less than G prime, and this less than can be any of our relations that we typically consider for graphs. It could be a new subgraph, it could be a subgraph, it could be minor, it could be topological minor. And this notion will change accordingly. Okay, is that a partial ordering on the infinite sets of graphs? It's reflexive, obviously, for each graph is less than or equal to itself. It's transitive, so if these all map into those, some of those, maybe we're not using all of them, and these map into something else, then these map into that. But it need be antisymmetric. So let's make it antisymmetric. So P is going to be called equivalent to P prime if and only if each is at most the other. That's a standard way of making quasi-orders into partial orders. So quasi-order just means reflexive and transitive, but not necessarily antisymmetric. Right. So now, then, this is a partial ordering on these equivalence classes. Right, and as before in the infinite chapter, I don't mean partial ordering in the strict sense that there must be a set that is partially ordered, but it's just reflexive, transitive, and antisymmetric. Okay, so much for the setup. Now What next? Yeah, but example, so if P is the class of all paths, right, all finite paths, and P prime is that of finite paths of even length, and less than or equal to is subgraph, then they're equivalent, right? Every path of even length is a subgraph of subpath, yes, because it is one. But also conversely, every path, even or odd, is a subgraph of some path of even length. So thinning out sensibly doesn't and shouldn't change this. So for example here, I could just take the stars with a number of leaves divisible by 7 or whatever, right? It wouldn't change the theorem that we had earlier, right? Every large enough, no. Okay, so that's what I wanted to say here. And now comes the definition. P1 up to Pn. And these are now, when I write curly P's, they're always going to be infinite sets of graphs. I write P because of property. Right? A property is a class of graphs that is closed under isomorphism, unless you take the view that that follows from the notion of class, but never mind. So since we're only considering generic embeddings, we're only talking about types, isomorphism types of graphs anyway. So I speak of the path of length 5, not the path on vertex Z 1 to 5 or 10 to 14 or something. Right? So you can think of them as isomorphism, the elements of these curly P's as isomorphism types of finite graphs, but infinitely many for every Pi. So that, finite collection of these Pi's is a Kuratowski set for a class curly C of sets P of no, not of, yeah, of finite graphs, obviously. If two things happen, for every P in curly C, there exists an I such that Pi lies below that P, right? Like in Kuratowski's theorem, the non-planar graphs. For every non-planar graph, there's one of those Kuratowski graphs below it. And I want these to be also of that kind. And second is it should be minimal, like K5 and K33, for I not equal j, pi is not going to be less than pj. Okay, so example. C is the class of all sets of connected graphs. As long as these are infinite, you can make them as sparse as you like. Take any infinite set of connected graphs. P1 is the set of stars. P2 is the set of paths. And now I'm claiming that this P1 and the P2, the set of all stars, the set of all paths, form a Kuratowski set for the class C of connected graph properties, of connected infinite sets of sets of infinitely many connected graphs. And we have to prove for that given any infinite set of connected graphs, either the set of all stars lies below it, or the set of all paths lies below it. Right? In this sense. So not necessarily the stars, but either the stars or the paths. And that is true, because if the stars didn't lie below that set, then it would not be true that all stars can be found in sufficiently high elements of P. If that is true, then there must be a cutoff. Then there are not even arbitrarily large stars, because if they're arbitrarily large, then all of them are found in there. So if there's a cutoff, then there exists some R above which no star is in any of those. But by our little proposition, if these graphs are big enough, they will contain either a star of that large order, which they don't, or a long path, so they must contain a long path. So from that R onwards, all PRs must occur here, because the stars with R leaves don't. So the entire class of all paths, P2, will be less than this particular P. Yeah. And we're requiring that the Kuratowski set is minimal in this obvious sense. We don't want any superfluous ones, and if Pi was less than Pj, then we wouldn't need Pj for this first point here. We could always use Pi below it. And that makes any such Kuratowski set unique. Why is that? Suppose that for some C, that's always unique as a Kuratowski set for some such C. And why is that? Well, if we had a different one, what does different mean? Unique up to twiddles, up to that relation. Right? If we had a different one, say Q1 to Qm, then one of these Qm's wouldn't occur, wouldn't be among those, not even equivalent to any of those. But such a Qi here would have one of those below it because these qi also satisfy this. They also lie in C. So we could use them or choose them to be this. And below any of this, there lies one of those. So below any qi here, there's one of these pj. But then vice versa, below any pj, there's a qi or ql. But then we'd have a ql below a qi, and that can't be. So if that all happens, then they're all equivalent. Right, so they're unique, and let me finish with the theorem that we have in fact proved. I just gave you the rephrasing in this terminology for the case of connectedness. So let Ck be the class of all infinite sets P of k-connected graphs. And I call that k-connectedness. Connectedness. So when I now say in the next 5 minutes, say k-connected in 2 minutes, k-connectedness, I mean this. Theorem. For k equals 1, 2, 3, 4, Ck, or k-connectedness, has the following Kuratowski sets. One, for k equals 1, we get the complete graphs, the stars, complete graphs, stars, and paths with respect to induced subgraph. And with respect to means that this denotes induced subgraph. And just the stars and the paths with respect to subgraph. For k equals 2, the Kuratowski, the unique Kuratowski set is the cycles and the K2Rs. Those are the two classes, right? Set of all cycles, set of all K2Rs are between 1 and infinity. With respect to topological minor, and 3 and 4. As I showed you with respect to minor. So here we have the wheels and the K3Rs, and for k equals 4 we have the double wheels and the K4Rs and the crowns and the Möbius crowns. Right, so it would be nice if you could sort of brood over this a little bit and see how this formalizes our earlier informal idea that, for example, the paths and the stars are the typical connected graphs in this Ramsey sense. Right? So it is a formalization. It's a bit of a mouthful if you look at all that. But I think it's a lean mouthful. It's sort of not unnecessarily complicated. It just captures exactly what we wanted to say.